Hi everyone. Today I will be presenting our work on fuzz testing of data analytics with framework abstraction. My name is Qian Zhang, and I'm a postdoc at UCLA working with Professor Mi-Young Kim. This work was done when the third and the fourth authors were PhD students at UCLA and UC Berkeley, respectively. In recent years, coverage-guided, mutation-based fuzz testing has emerged as one of the most popular and effective test generation techniques for large software systems. For example, the American fuzz loop, which is also known as AFL, it is a popular fuzzing tool for C and C++ programs, and it finds numerous errors. So in fact, most fuzzing techniques start from seed inputs. They generate new inputs iteratively by mutating the previous inputs and add new inputs to the input queue if they exercise a new branch. Such fuzzing techniques are based on the implicit assumption that it takes a relatively short amount of time to repetitively run program on the test with different inputs. Emerging technologies are producing much data, and the importance of data-centric applications continues to grow. Data-intensive scalable computing systems, such as Apache Spark, Apache Hadoop, are becoming widely available to industry. These platforms process the input records in batches with short tasks, and each batch or each partition dataset is called an RDD. Data analytics programs are comprised of a relational skeleton of data flow operators and custom logic as user-defined functions. Although these programs look small, but the compiled bytecode include the entire framework, for example, 700,000 lines of code for Apache Spark. That means data flow implementation contributes most of the bytecode. So in this case, how to test such programs efficiently? Our experience tells us that fuzzing cannot be easily applied to big data analytics directly. While traditional fuzzing techniques assume thousands of invocations per second, big data analytics applications, such as Apache Spark applications, would need about 19 seconds to initialize the Spark context for each run. Such long latency prohibits the applicability of fuzzing for efficient test generation. Prior work finds that branch coverage is an effective guidance mechanism for feedback-guided fuzz testing, pushing test generation towards hard-to-reach corners. So basically, it instruments the program's bytecode to label each branch. However, it cannot differentiate user-defined functions from framework code, and thus it pushes test generation naively towards exploring the internals of the ASE framework as opposite to application logic. And also, it cannot effectively monitor different equivalence classes of data flow operators in which numerous errors originate from untested equivalent classes. Last but not least, random binary mutations in existing fuzzers often generate inputs that fail at the entry point without exercising code further, so that it can hardly generate meaningful data that will lead to a realistic application bug. To tackle these challenges, we propose BigFuzz, which has three novel components to make coverage-guided fuzzing tractable for big data analytics. Our key insight is that we can reduce the long latency of big data analytics applications by abstracting the data flow implementation in the framework using executable specifications. And we can focus on analyzing the application logic rather than the entire framework coverage. So to do so, first, we eliminate the dependency of a data-intensive scalable framework to get rid of the long latency by abstracting the data flow implementation using a source-to-source transformation with extracted user-defined functions. Second, based on the transformed program in specification, we monitor a combined equivalence class-based data flow coverage and control flow coverage of extracted user-defined functions. Then during fuzzing, we design mutations that are specifically for big data analytics based on our empirical study of common error types in real-world big data analytics applications. For the framework abstraction, BigFuzz decomposes a big data analytics application into two components: a directed acyclic graph of data flow operators and a list of corresponding user-defined functions. We can look at this figure A. This is an example of an original Spark program. It contains a map operator followed by the filter operator, and the highlighted code areas are their corresponding user-defined functions. We map each data flow operator's implementation to the corresponding simplified yet semantically equivalent implementation that can be invoked numerous times in the fuzzing loop, which we call executable specifications. BigFuzz automates this procedure in two steps: UDF extraction and source-to-source transformation. In the first step, BigFuzz decompiles the bytecode of original application into Java source code and traverses the abstract syntax tree to search for a method invocation that is corresponding to each data flow operator. The input arguments of such method invocation represent the user-defined functions. For example, this figure B is the extracted user-defined function for the map operator, and we store the extracted user-defined functions as separate Java classes. Then in step 2, BigFuzz uses the DAG extracted in the previous step to reconstruct the program in the same interconnected data flow order using executable specifications. For example, figure C is a transformed program which retains the order of data flow operators, and figure D is the equivalent specification implementation of a map operator. Such spec implementation takes in an ArrayList object as input to simulate the RDDs in Spark data flow operators. So it applies the corresponding user-defined function on each element of the input list and returns an output ArrayList. Currently, BigFuzz is designed for data analytics programs using Apache Spark, but its key idea can be generalized to other data-intensive scalable computing frameworks such as Hadoop as well. Branch coverage is an effective guidance. However, we observe that it is not an ideal guidance mechanism in big data analytics because branch coverage cannot represent the semantic meanings of data flow operators. For example, when testing operator filter, it is important to test two equivalence class cases. One terminating case when the filter predicate holds false, thus the data records stop at this filter, and one non-terminating case when the filter predicate holds true for at least one data record. Many prior studies argue that numerous errors originate from the untested equivalence classes of data flow operators. For example, suppose that we are filtering data records based on the zip code column. So when the input is mutated to 90000 and 90095, it doesn't exercise a new branch, but it leads to an previously untested terminating case in which none of the data records passes the filter. Different from binary mutations, which randomly flip several bits or several bytes, we perform coarse-grained, record-level mutations based on a user-defined schema in which a user can define the number of columns, data type, and value range for each column. Then, BigFuzz uses 6 kinds of mutations that mimic real-world errors in big data analytics applications. They will modify data with respect to the structured data types as well as value ranges. For example, the data distribution mutation can change the value of an integer column to either a valid or invalid value, while the data type mutation, for example, can change an integer to a float type that result in a type mismatch exception. Given a seed input, BigFuzz will either randomly mutate the seed input or randomly generate valid inputs followed by mutating such inputs to increase cumulative coverage. You may be wondering where these mutation operators are coming from. So these mutations are based on our empirical study of common errors that appear in real-world big data analytics applications. The study is based on Stack Overflow and GitHub, in which we searched for the keywords that are related to both Apache Spark and Apache Hadoop. We manually looked into all of these posts and we classified the errors into 10 common error types. For example, when the program tries to access a non-column, it will lead to an incorrect column access, or the data records are delimited by a comma when a space is expected. We performed a wide range of systematic experiments to evaluate BigFuzz performance in terms of individual improvements from each optimization on a set of open-source big data analytics programs. In the rest of time, I will talk about the 4 main evaluation scenarios to highlight BigFuzz's contribution towards big data testing. For the applicability, we want to answer whether the widely used fuzzing tool such as AFL is applicable to big data analytics programs. The answer is no. We take AFL as an example. We're using AFL with 9 GB as memory and 100 seconds as timeout setting. It runs at an extremely low speed and crashes after 70 executions in average. To evaluate the Speedup with framework abstraction, we use a downgraded version random fuzz M, which retains the error type guided mutations without source-to-source transformation for framework abstraction. In such case, in random fuzz M, each fuzzing iteration needs to set up a Spark context. We ran both tools for 1000 iterations to record the execution time. We repeat the experiment for 10 times and report the averages in this figure. So we can see that BigFuzz can achieve up to 1500 times speedup with a framework abstraction. To evaluate the covered GDU path and the corresponding error detection capability, we use 12 open-source big data analytics programs, and we automatically seed 52 errors in total to these programs. For the baseline, we use a downgraded version random fuzz A, which retains the framework abstraction without error type guided mutations. In such case, random fuzz A uses the conventional binary mutations to generate inputs. For each subject program, we want to know, after 1,000 iterations, how many JDU paths we can cover and how many injected errors can be detected. This table shows the summary of results for these 12 subjects. For each subject, we run 10 times and get the average results. BigFuzz provides up to 3.7 times improvement on code coverage and achieves up to 2.5 times improvement on error detection capability. We then evaluate how much improvement in applicability and error detection we can achieve compared to an alternative symbolic execution-based technique, BigTest. So BigTest is only applicable to 6 of our 12 subjects. For these 6 subjects, BigFuzz detects 80% more injected errors on average. Thanks to all the support of this work. To sum up, we adapt fuzz testing to big data analytics applications with long latency. So specifically, BigFuzz had 3 novel components: a data flow abstraction using source-to-source transformation to tackle the long latency, a tandem monitoring of equivalence class-based data flow coverage with control flow coverage in user-defined functions, and an application-specific mutation that mimics real-world error tags in big data analytics programs. Thank you.